Hi everyone. So today we're going to be talking about a new topic called optimization. And so optimization is basically going to be like an application of the types of problems that we've been working on for a while now. So optimization problems will basically involve finding a maximum or a minimum value. And so the kind of challenging part of optimization problems are usually kind of coming up with what's the function that you're trying to find the maximum and minimum of. And then once you have that function, it becomes a matter of just using calculus the way that we've been doing to figure out what is the maximum or minimum. So you might notice that we're kind of skipping sections. So we're going to come back to section 4.4 next week. I just think that optimization kind of fits better after section 4.3 than later on. Okay, so we're going to start with an example that is not really an example where you have to use calculus, but I just think it's a good example because you can really kind of visualize why we can do things the way that we can. So let's say that you threw a ball up in the air, and the height of the ball after t seconds is given by the function h of t is equal to negative 2t squared plus 6t plus 5. And if you've taken any physics, you'll know that this is not an accurate equation for throwing a ball up in the air, at least not on the planet Earth, but let's forget about that for now. So the question that we're going to answer is we're going to find the maximum height of the ball, and then also the time when it reaches that height. Okay. So if we think about it, what kind of a shape are we dealing with? If we think about like how this ball is kind of traveling as time goes on, the graph we have is a parabola, right? And I'm not going to even attempt to draw this parabola accurately. I'm just going to draw like a quick sketch just to give us an idea of the kind of shape we're dealing with. So we know it's an upside down parabola. Basically, that's really all we need to know in order to answer this question. So just looking at the graph, what is the highest point on, that the ball is going to reach? Well, it's going to happen at the vertex. So you don't need calculus to answer this. You could answer this question actually in like an algebra class where really all you're trying to do is find the vertex of a parabola. But let's say that you didn't know how to find the vertex of a parabola. So how could you go about figuring out what that highest point is on this graph? Well, you can look for the place where the derivative is equal to 0, right? Because anytime you have a local max or min, which kind of gives you this peak shape that you're going for, that's going to be a place where the derivative is equal to 0. So to find the maximum, we're going to find h prime of t, and we're going to set it equal to 0. So if we take the derivative of h of t, we get h prime of t is equal to negative 4t plus 6. And then if we set that equal to 0, we get negative 4t is equal to negative 6. And so that tells us that t is equal to negative 6, negative 6 over negative 4, which simplifies to 3 over 2. So, we have a picture of this graph right in front of us, or at least a rough sketch of what it looks like. So we know that it's going to be a maximum, right? We know that when you have an upside down parabola, like we have here because of that negative sign, we know that that means that the vertex is going to be a maximum and not a minimum. But now that we have the second derivative test, we have like a nice, quick, easy way to just double check that the thing that we found is in fact a local max versus a local min. So how can we do that? Well, if we take the second derivative we get just -4. Right, so this, the derivative of -4t plus 6 is -4. And so that tells us that this function is always concave down. So if we were to plug in 3/2, we would get a negative number. And so that confirms the fact that we have a local max, which in this case happens to actually be the entire maximum value of the function, but it's also a local maximum. And that's kind of the key idea that we're going to be using here, is that the types of functions we're going to be finding the max or the min of will typically be functions where the local max or local min is also the absolute max or absolute min. So local max and min just means, places where the tangent line is 0. And if you have a graph that's shaped like this one, that also just happens to be the very highest point on the graph. Okay, so we haven't quite finished answering this question, right? We've so far figured out that at t is equal to 3/2, we have a local max. So in order to actually answer the question, which asks us what is the maximum height, we need to plug in 3/2 into our original function. So if we plug this in, and I actually forgot to do this ahead of time, so I'm going to do it on my calculator real time. So I'm plugging in 3/2 for, I'm just going to write it out as a fraction. I think that'll actually be faster. So we have -2 times 3/2 squared, plus 6 times 3/2 plus 5. So that's going to give us -2 times 9/4 plus, so 6 times 3/2 is going to be 18/2 plus 5. So that's going to simplify to, so -2 times 9/4 is going to be the same as actually -9/2, right? Because we can simplify this to be 2. So we have -9/2 plus 9 plus 5. So that's -9/2 plus 18/2 plus 10/2. So I guess I shouldn't have simplified that 18/2 earlier, but that's okay. And so altogether this gives us, so let's see, that's 28 minus 9, right? Am I getting that right? 18, yeah, so it's 19/2. So that tells us that the maximum height reached by our ball is 19/2, I guess, feet. Maybe I didn't specify the units here. Let's say the height in feet. So our maximum height is 19/2 feet, and that happens at a time of 3/2. Okay, so just to kind of summarize, because I know there's a bunch of different ideas floating around here. Because this is a parabola, technically you don't need to use calculus. Technically you could just find the vertex, but the problems that we'll be working on moving on from here are not always going to be parabolas. So this general kind of process will work for those as well. So we'll always be finding the derivative, setting it equal to 0 to find critical numbers. And then once you have those critical numbers, just double checking that they're actually maxes or mins using the second derivative test, and kind of going from there to finish answering the question. So there's one step that we didn't have to do in that problem that is going to become really, really important in these next problems. So I want to write out some general steps for solving these optimization problems, and then we'll jump straight into another example. So steps for solving optimization problems. So the first step, and this is a step that I think a lot of people are maybe a little hesitant to do. You want to just kind of jump right into solving something, but I think this is really, really important. The first step I want you to always do in these questions is I want you to be able to express in a sentence, in words, what is it that you're trying to maximize or minimize? Because if you can't describe, and we'll see, in a minute why this is necessary. In the previous question we did, the equation was just given to you. But in the equations that or the problems that we're going to work on, you're not just going to be handed, oh, hey, find the maximum of this function. You're going to have to kind of figure out what that function is. And so to figure out what that function is, it's really, really important that you first start by expressing in words what it is, like what are you trying to minimize or maximize. So if that doesn't really make sense right now, that's okay. Well, when we do an example, I think you'll see why I'm adding this as a step, or I should say minimize or maximize. So in the problem that we just did, like I said, this step isn't so important in that problem, but what were we trying to maximize? We were trying to maximize the height of the ball. And in that case, we just happened to already have a function given to us for the height of the ball. So the second step is going to be to write a function for the quantity that you described in the first step. Whatever it is that you're trying to maximize or minimize, you need to be able to write that down as a function. And so again, to talk about the previous question that we just did, we were given a function, but maybe if we weren't given it, you would have to kind of somehow cook up, what is that function? What is the function that tells me the height of this thing? So the next step is going to be to find critical numbers of the function that you found. And then the fourth step is to use the second derivative test to confirm that you're finding a max or a min, depending, and we'll see that there's some problems where you're trying to find a minimum value, some where you're trying to find a maximum value. And then the last step is basically to look at what you're actually being asked. So what do I mean by that? Well, in this question that we did here, if you got to this point and you're like, okay, t is equal to 3/2, that's the answer, you would actually get this question wrong, right? Because the question was not asking, that was part of the question, but really the main thing the question was asking was to find the maximum height. And so it was really important in answering this question that you took that time and plugged it back into the question, plugged it back into the function to figure out what that maximum height was. So that step is going to be really important as well. So basically, make sure you're answering the question that's being asked. And so that will really vary depending on what is the type of question you're working on. Okay, so let's look at an example. So what we have here is a parabola, but we're not going to be actually finding the maximum value of this parabola. We're going to be kind of doing something related to this parabola. So the question that we're going to be answering here is we're going to find the point that lies on this parabola that is closest to the point 0, 2. So the point 0, 2 would be this point here. So we're going to find the point on the graph of this function, the parabola that's graphed here is negative x squared plus 4. And we're trying to find the point, or we'll see actually there's going to be 2 points that satisfy this. And let me just neaten this up a little bit. So that are closest to the point 0, 2. Okay, so let's draw kind of like a sample point just to see what we're talking about here. So like, for example, if this was your point, I'm just going to label this x, y, because it's just some generic point. We're looking for the point and I'm not saying that this is necessarily that exact point, but we're looking for some point on this parabola that is as close as you can get to this point in purple. So for example, a point that's down here would be a lot further away, right? So, somewhere near where I drew it is at least around the correct thing. Again, like up here would be even further away, right? So we're looking for the point that is basically as close as you can get to the point 0, 2 while still staying on the parabola. So let's kind of go through those steps that we established on that previous question or on that previous page. So the first step we want to do is we want to be able to express in words what is it that we're trying to maximize or minimize. And so this is a great example of a problem where it's really, really important to actually be able to say it in words. So what would not be the correct thing would be to say, oh, we're trying to maximize or minimize y is equal to negative x squared plus 4. We're not, right? The question is not asking us to find the maximum or minimum value of the parabola. It's asking us to find a point that's close to another point. So what kind of thing are we trying to minimize here or maximize? We're talking about distances, right? And because we're looking for the points or point that are closest, that tells us that we're trying to minimize the distance. So we're trying to minimize the distance from the point 0, 2 to a point xy on the graph of y is equal to negative x squared plus 4. Does that make sense? So because we're looking for a point that's closest, that means that the thing we're trying to minimize is actually distance. Okay, so the next step is going to be to actually write a function for distance. And I'm going to switch colors because we need a little color in here. So how do you write down the distance between 2 points? Well, we can use something called the distance formula, right? So the distance formula says that the distance between 2 points, and actually maybe let me write this down as kind of a side note. Let's put it down here somewhere. So reminder, if you are trying to find the distance between 2 points, and let's say those points have coordinates x1, y1, and the second point has coordinates x2, y2, the distance between those 2 points is going to be the square root of, and you subtract the two x coordinates, so x2 minus x1. Doesn't matter what order you subtract them, you're just subtracting them in either order and squaring it, and then subtracting the two y coordinates. And the distance formula actually comes directly from the Pythagorean theorem. I don't really want to go into that in this video because it's kind of more of like a pre-calculus topic, but basically if you draw 2 points and you draw a triangle, like kind of connecting the 2 points and then going horizontal and vertical between the 2 points, you'll see that the Pythagorean theorem actually just basically leads you directly to the distance formula. So we're going to use this in our question up here. So the distance between these 2 points is going to be the square root of, and then we're going to subtract our x coordinates and our y coordinates. So this was the point 0, 2. So it's going to be, for the x coordinates, we can say x minus 0 squared, right? Because our x coordinate of that point is 0. And then the y coordinates are y minus 2 squared. So this is the same thing as x squared plus y minus 2 squared. So there's one issue here, which is that so we're trying to find a function that we can actually use calculus to find the minimum or maximum of. And we only know how to deal with functions that are functions of only one variable, Right now, this is actually a function of two variables. And so this isn't something that we talk about in this class, but in future classes, you might see functions that are written like this, where you're saying, okay, it's a function where I have to input both an x value and a y value to find, whatever the result is. So we want to find a way to translate this into having only x's. And this is a step that's going to come up actually in a lot of these optimization questions. So how can we rewrite this so that it only has x's in it? Well, we know that if the point xy lies on our graph, we know that the equation for this graph is y is equal to negative x squared plus 4. And so that means that the y-coordinate of this point can actually be written as negative x squared plus 4, right? So let me write that down here. So y is equal to negative x squared plus 4 because it lies on this graph. And so what that tells us is we can now go in and replace where it says y, we're just going to replace that with negative x squared plus 4. So let's just clean that up a little bit. So we now have x squared plus, and this simplifies to negative x squared plus 2 squared. So we can multiply out this second part, and we'll do that in a minute, but there's one other thing I want to point out. And this is going to be another kind of important fact that we'll use in these optimization problems. We're trying to find the minimum value of a square root of some stuff, right? So there's going to be some numbers underneath this square root, and we're trying to find the minimum value of the square root of whatever that is. So if you're trying to minimize a square root, that's equivalent to minimizing the stuff under the square root, right? Because, for example, like square root of 16 is bigger than square root of 9. And square root of 25 is even bigger than square root of 16. And how can you tell? Well, it's because 25 is bigger than 16 and 16 is bigger than 9. So the bigger the stuff underneath the square root, the bigger the square root. And I guess actually we're trying to minimize, right? So the smaller the number under the square root, the smaller the square root is. And so this problem would totally work if you used calculus to find the minimum value of this function. You could say, d of x is equal to this and find the minimum, and it would work. But it would be a lot of tedious algebra because of the square root. It would just make the derivative harder to take. And what I'm saying here is that rather than focus on finding the minimum value of this whole thing, we can focus on finding the minimum value of the stuff inside. Because the stuff inside, if we can make that as small as possible, well then the overall square root will also be as small as possible. So basically, instead of minimizing the square root of something, I'm just writing stuff, here we have x squared plus all that stuff, you can minimize stuff, right? You can just minimize the thing that's underneath the square root. So the function that we're actually going to minimize here, and I'm just going to move this down, hopefully far enough. Okay. So we're going to focus on instead minimizing the function. We can call our function d of x is equal to x squared plus negative x squared plus 2 squared. So hopefully you're all still with me. I know there's kind of a lot of different steps here, but yeah. So again, just to quickly recap, the steps we did is we figured out that we wanted to minimize the distance from 0, 2 to this point on our graph. So we wrote down the distance formula and we're like, okay, cool. We want to find the minimum of this distance. But then we realized, well, we can't really do calculus on this because we only know how to do calculus on functions with one variable. So we decided that, okay, we can replace this y with negative x squared plus 4 because that's the relationship between x and y on this graph. And so that gave us a function that only had x's in it. And that would have been something that was fine to minimize, but in order to make this problem easier, instead we decided to minimize the stuff inside the square root. Okay, so let's now just clean this up a little bit, and then we'll get to work with using calculus. So if you were to multiply out the stuff that we have here, you would get, so negative x squared squared, so multiplied with itself is going to give us x to the fourth. And then we would get negative x squared times 2, and then another negative x squared times 2, so that's going to be negative 4x squared. And then we're going to get plus 4. So we can combine like terms, and we have x to the fourth minus 3x squared plus 4. Okay, so this is the function that we want to minimize. So this is what we're going to focus on minimizing. So how do we find the minimum value of something? Well, now we can jump into the third step, which is finding the critical numbers. And then once we have the critical numbers, then we can figure out, confirm that things are what they're supposed to be in terms of being local maxima or minima, and then go from there. So the derivative of this thing is going to be 4x cubed minus 6x. And so we want to set that equal to 0. So we can divide everything by 2, first of all, and that gives us 2x cubed minus 3x is equal to 0. And now we can factor out x from both of them. So we get x times 2x squared minus 3 is equal to 0. And that gives us two options. Either x is equal to 0 or 2x squared minus 3 is equal to 0. So if we solve this equation over here, we get 2x squared is equal to 3. So x squared is equal to 3 halves. And so that means that x is equal to plus or minus square root of 3 halves. And I still need to move this further, apparently. Sorry about that. Okay, so these are our two critical numbers. So now we want to double check whether these are maxima or minima. And so how can we do that? We can plug them into the second derivative. So the first derivative we just found was this, right? 4x cubed minus 6x, 4x cubed minus 6x. So sorry, I can't seem to get them to stay on the page on the same place, or to both be on the page at the same time. Let me try one more time. Okay, there we go. So the second derivative is going to be 12x squared minus 6. So now we can double check like what we get when we plug in our two numbers. So if we plug in 0, we get 12 times 0 minus 6. And so that tells us that this is actually a local max. So that means that this answer is no good. This is not actually the answer we're looking for. We want to make sure that the answers that we're finding are local mins. So if we plug in square root of 3 halves, we get 12 times square root of 3 halves squared minus 6. So that's going to be 12 times when you square this, it becomes 3 halves. And so that's the same thing as, so 12 times 3 halves, we can simplify, we can write this as 6 and get rid of that. So we have 18 minus 6, which is 12. And 12 is positive, and so that tells us that the graph of the derivative is concave up. And so that means that we have a local min. And I'm not going to do it for negative square root of 3 over 2 because you'd get the exact same thing. Maybe I'll even put in the plus or minus here, right? Because you're squaring it, so the plus or minus isn't going to matter. So that tells us that that is the x value we're looking for. So let's go back up at our graph and kind of see where that point would lie. So square root of 3 halves, let me just see what that would approximately be. So square root of 3 halves is approximately equal to 1.22, I'll just say 1.22. So basically actually pretty close to where I drew it, right? So 1.22, and then we also would have negative 1.22. So basically we found a point that is somewhere around like probably more like here, and another point that is somewhere like here are our 2 points that are closest to 0, 2. So the last step is we need to make sure we're actually answering the question. So the question is asking us to find the points on the graph. So we found the x coordinates of the point. We now need to find the y coordinates of the point. So how do you find the x coordinate, or if you know the x coordinate of a point, how do you find the y coordinate? Well, you plug it into your equation, right? Not the equation we're trying to minimize, but the actual equation of the graph, because that's what we're looking for, or that's what we're looking at, I guess I should say. So to actually kind of finish off this question and find what's asked of us, we now want to find, so our equation was y is equal to negative x squared plus 4. So if we plug in x is equal to negative square root of 3 halves, we're going to get y is equal to negative square root of 3 halves squared plus 4. So that's going to be negative 3 halves, because the negative on the inside cancels out because you're squaring it, plus 4. And so that's going to give us, so 4 can also be written as 8 halves. And so that tells us that we have 5 halves is the y coordinate. And this is just still in the way. And then we'd get the same thing when we plug in the positive, right? So I can actually say plus or minus here, because regardless, because we're squaring it, it's going to give you the same result. So that tells us now we're finally ready to answer this question. The 2 points on the graph of y is equal to negative x squared plus 4 that are closest to the point 0, 2 are the points negative square root of 3 over 2, comma 5 halves, and positive square root of 3 over 2, 5 halves. So I know that was a lot. There's a lot of steps in this, but I think really just keep focused on what it is that you're actually trying to do. I think the very easiest way to get mixed up here is to just jump straight in and just the first equation you see, just say, okay, I'm just going to find the derivative of that. We never found the derivative of this function, right? This function had nothing to do with derivatives. Really, the only way that we used this equation was to figure out the points on the graph. Really, the thing that you're taking the derivative of is always related to step 1, right? Step 1 where you write down what is it that you're trying to minimize or maximize. Okay, so we're going to do one more question. And then in tomorrow's video, we're going to do some more examples. So today we're doing examples that are kind of more like related to graphs. And then tomorrow we'll do some that are more like word problems. So this one, again, we have a graph here, but we're not actually finding the maximum or the minimum of this function that's in this graph. This time we're going to be drawing a rectangle under this graph and trying to find the maximum area of a rectangle that you could fit under the graph. So for this one, we're finding the maximum possible area of a rectangle with its bottom edge on the x-axis and top 2 vertices on the graph of, so this function that we have graphed here is y is equal to e to the negative x squared. So what is this question asking us? It's basically saying if we draw a rectangle that has its top 2 points lying on the graph, so they're kind of symmetrically across from each other because it's a rectangle, it has to be a straight line, and then we kind of draw straight down like this. So we're looking for what's the very biggest rectangle that we could possibly get. So what would some other possible rectangles look like? So that I just drew kind of one example, but like this would be another rectangle, right? That would be another rectangle that has its vertices on the graph and the bottom edge on the bottom, or you could have a rectangle that looks like this. So personally, looking at these options, I kind of like would predict that the purple one is the biggest, right? So I think, we're looking for some kind of a middle ground, right? Because if you make your rectangle like really like the blue one, then it's going to become very thin and not have very much area. And then similarly, if you have one that's really tall, it's going to become very thin and not have much area. So it's going to be something kind of in the middle, kind of like the purple one that we drew. Okay, so again, we want to start by writing down concretely, what is it that we are trying to maximize or minimize? So in this case, we're trying to maximize the area of the rectangle that we've drawn here. So what that tells us is that in the next step, that's what we're going to need to write a function for. We're going to need to figure out what's a function that would give us the area of this rectangle that we've drawn. So this is where the actual equation of this graph is going to come in. So like we said, this graph has the equation y is equal to e to the negative x squared. So if we have, we have these two kind of corners on the graph, let's focus on the one that's in the positive side. So this is like some point, right? So we could call this point xy if we wanted to. And we'll see that just like with the last one, we're going to be able to kind of do a little better than writing down xy, but let's start with xy. So if this point is xy, that means that this distance here is x, right? Not the distance across the whole bottom of the rectangle, but just like the positive part. And this distance here is y. So what would the area of this rectangle be? Well, if this distance here is x, then the entire distance all the way across would be 2 times x, right? Because x is just telling you the distance from 0 to the x coordinate. So the area would be equal to 2x times y. Because how do you find the area of a rectangle? You do base times height. The base is 2x, the height is y. But just like in the last question, we want to do a little bit better than that. So because y is equal to e to the negative x squared, instead of writing y here, we can write this point as x comma e to the negative x squared. And so if we replace the y that we have there with e to the negative x squared, now we have a function of x, right? Now we have a function that only has one variable in it, and we can use calculus on it. So we're trying to find the maximum value of that function. So that's the function that we're going to work with, that we're going to take derivatives of. We're not taking the derivative of this. We're not looking for the maximum of that. We're looking for the maximum of this function. So let's do that. So we want to start by taking the derivative. So a prime of x, I'll switch colors here. So we're going to have to use the product rule. So the product rule tells us, so we start by taking the derivative of 2x, and that gives us 2. And then we leave e to the negative x squared alone. And then the second part of the product rule, we leave 2x alone. And then we multiply that by the derivative of e to the negative x squared. So what's the derivative of e to the negative x squared? Well, we have to use the chain rule. So the first part of the chain rule just kind of repeats e to the negative x squared. And then we multiply by the derivative of the exponent. So what's the derivative of negative x squared? It's negative 2x. So we can simplify this to 2e to the negative x squared minus 4x squared e to the negative x squared. Okay, so now we're going to set this equal to 0, right? Because we're trying to find the critical numbers of this function that we're trying to maximize. So we can factor out 2e to the negative x squared from both, right? Or we could even maybe start by dividing everything by 2. So if we divide everything by 2, we're left with this. and now we can factor out e to the negative x squared. So we're left with, if we do that, 1 minus 2x squared. So now we have two possibilities, either e to the negative x squared is equal to 0, or 1 minus 2x squared is equal to 0. So we've seen quite a few times now that if you have e to a power, that's never going to equal 0. So that one doesn't give us any solutions, but we can solve this one. So this would give us 1 is equal to 2x squared, or 1/2 is equal to x squared. And then that's going to tell us that x is equal to plus or minus square root of 1/2. So in this case, even though we have this plus or minus, let's just take the positive one. And so the reason I'm saying that is that it doesn't really matter which one you choose, but we kind of chose to make x be like this distance here, right? So we really just want x to be a positive number, and this point will be included because when we find the actual area, we're going to do 2 times x. So x itself just represents this x coordinate. But when we go to actually find the area, we're going to do 2 times x. So let's just take the positive one. So we're going to just focus on the positive one. So the next step is to double check that that actually gives us a local max, right? Because we want a maximum in this problem. So how do we do that? We take the second derivative. So it's going to be a little bit messy in this case. So our first derivative was basically this thing, right? So the second derivative is going to be 2e to the negative x, right? That part is, or negative x squared, that part is staying the same. And then we have minus, and now we can do the product rule again. So the derivative of 4x squared is 8x. And then the derivative of, then we leave 4x squared the same, right? So, and maybe let's be careful here. Let's lump this negative sign in with the 4x squared. That way we won't have to worry about parentheses. So the negative sign was here, and then we're also going to have a negative sign on this next part because this next part is just leaving the first part alone. And then the derivative, as we've seen, of e to the negative x squared is e to the negative x squared times negative 2x. So that simplifies to 2e to the negative x squared minus 8x e to the negative x squared. And then this part becomes minus 8x cubed e to the negative x squared. So for the sake of time, I'm just going to tell you that if you plug in square root of 1/2, you get a positive number. Or sorry, let me think about, no, sorry, negative. You get a negative number. Because I just know that the result we're getting is actually a maximum. So just trust me that it's negative. If you want to confirm that for yourself, you can go ahead and plug in square root of 1/2. And basically what you'll see happen is that you can kind of see it here, right? All of these have the same exponent. So those are all going to become e to the negative 1/2. And then really that will allow you to then group everything else together, and these will both be negative. So you have like 2, and then that's 2 other negatives being subtracted. So that's going to give you overall a negative result. And so because it's a negative result, that tells us that we have a local max, and that's good. That means that we actually found the place where a maximum value occurs. Okay, so last step on this one is actually looking at, what is the question asking us? So the question was not asking us, find x. The question was asking us to find the maximum possible area. So we need to go back to that question and figure out what is that area. So the area was going to be equal to 2 times the x value that we found times the height, and the height was e to the negative x squared. So we can just kind of go and plug our number into that. So we know that the area, I'm just going to write it down here so we have it, is going to be 2x times e to the negative x squared. So if we plug in the number that we found here, so square root of 1/2, we get 2 times square root of 1/2 times e to the negative square root of 1/2 squared. And so we can write this square root of 1/2 a slightly nicer way that will let us kind of combine stuff. So we can rewrite this as 2 times 1 over root 2, right? Because square root of 1 over square root of 2 is the same as square root of 1/2, and square root of 1 is just 1. And then we have e to the, and so if you take the square root of 1/2 and square it, that just becomes negative 1/2. So we're basically there. There's just a few ways that we can clean this up even more. So we can now rewrite this as 2 over square root of 2 times, and then e to the negative 1/2, that's the same thing as 1 over the square root of e. And then 2 over the square root of 2, well, if you rationalize the denominator, you'll see that that's actually just the same as square root of 2. So we have square root of 2 times 1 over square root of e, so that's square root of 2 over square root of e, or you could even write that as square root of 2 over e. And so that is the maximum area, whatever that is as a number. And maybe let's just check in. So square root of 1/2, where does that lie? Well, the square root of 1/2, let me see, that's I think approximately like 0.7. Square root of 1/2 is, yeah, 0.71. So, you know, the rectangle we drew here was pretty good. The rectangle that would give you the biggest area would be probably a little bit further this way. But like we said, it kind of has to be this like middle ground in terms of not being too long and skinny or tall and skinny. Okay, so yeah, I know these were both definitely kind of challenging examples. So the worksheet today has, I think, just going to be like 3 more examples for you to try. And then in tomorrow's video, we'll do even more examples with working with optimization. So definitely recommend really try to follow the steps that I outlined in this when you're doing them. I think otherwise it can get kind of overwhelming to figure out what to do first. So I think it will be helpful if you follow the steps that I wrote down. All right, I will see you next time.